Test for sequence fnx equals to n square x upon 1 plus n cube into x square for uniform convergence over close interval 0 to 1. Solution here: fnx equals to n square x upon 1 plus n cube into x square. F of x equals to limit n tend to infinity n square x upon 1 plus n cube x square into x square. So limit dividing both side numerator and denominator by n cube, so x upon n upon 1 upon n cube plus x square equals to 0 for all values of x. Now f n x minus f of x equals to n square x upon 1 plus n cube x square minus 0 modulus equals to modulus of n square x upon 1 plus n cube into x square. Let y equals to n square x into x upon 1 plus n cube into x square. Then dy upon dx equals to 1 plus n cube x into n square minus n square x into 2 n cube x upon 1 plus n cube x square whole square equals to n square plus n raised to power 5 into x square minus 2 n raised to power 5 into x square upon 1 plus n cube into x square whole square equals to n square minus n raised to power 5 into x square upon 1 plus n cube into x square whole square. For maximum and minimum, dy upon dx equals to 0, so n square minus n raised to power 5 into x square equals to 0, which implies dy n square into 1 minus n cube into x square equals to 0, which implies 1 minus n cube into x square equals to 0, which implies n cube into x square equals to 1, which implies x square equals to 1 upon n cube. So x equals to 1 upon n raised to power 3 upon 2. Also d square y upon dx, dy upon dx again derivative, so d square y upon dx square equals to 1 plus n cube into x square whole square minus 2 n raised to power 5x minus n square minus n 5 into x square into 2 into 1 plus n cube x square into 2n cube x upon 1 plus n cube into x square whole raised to power 4 equals to 2 into n cube x taking common into 1 plus n cube into x square into n square into 1 plus n cube into x square plus 2 into n square minus n raised to power 5x square upon 1 plus n cube into x square whole raised to power 4, cancelling 1 plus n cube into x square from this term, so equals to minus 2 into n cube into x into n square plus n5 into x square plus 2n square minus 2n square into x square upon 1 plus n cube into x square whole raised to power 3 equals to 2n square into 3n square minus n raised to 5x square upon 1 plus n cube into x square whole cube. Now d square y upon dx square equals to at x equal to n raised to power 3 upon 2 equals to 2n cube into 1 upon n raised to power 3 upon 2 into 3n square minus n raised to power 5 into 1 upon n cube upon 1 plus n cube into 1 upon n cube whole cube equals to 2 into n raised to power 3 upon 2 into 3n square minus n square upon 1 plus 1 whole cube equals to minus 4 into n raised to power 7 upon 2 upon 8 equals to minus n raised to power 7.2 upon 2 is less than 0. So which shows that y is maximum when x equals to n3 upon 2 and maximum value of y equals to n square upon n square into x upon 1 plus n cube upon x square equals to n square into 1 upon n raised to 3 upon 2 upon 1 plus n cube into 1 upon n cube equals to n raised to 1 upon 2 upon 2, so equals to square root of n upon 2. Also x equals to n raised to power x equals to 1 upon n raised to power 3 upon 2 tends to 0 as n tend to infinity. So mn supremum of x belongs to close interval 0 to 1 modulus fn x minus f of x equals to supremum x belongs to close interval 0 to 1 modulus of n squared x upon 1 plus n cube into x square minus 0. So equals to supremum x belongs to close interval 0 to 1 and modulus of n squared x upon 1 plus n cube into x square equals to square root of n upon 2, which does not tends to 0 as n tend to infinity. Hence the fn does not converges uniformly on close interval 0 to 1.